like max headroom.
Until I set up refreshing my snort rules on my server. It's a cron job. Here's one.
All right. So it is time. It's 10:30. I'm going to get started. I'm glad so many people can make it today because I noticed the campus is a little bit more quiet today. I wonder why. Exactly. That would be a good question. Okay, so we are still on the topic of propositional calculus, which is related to propositional logic. Okay, so those two are definitely related. One is kind of much a more formal way to describe the system, which is the calculus. Propositional logic is really just the rules, the axioms, and that will help you derive from one form to another form. So what we'll do today is to finish this up first. Okay, so this is still a pretty long topic, and some of you or many of you will have questions. So don't hesitate to raise your hand and ask questions when you do have questions. Okay. I think last time we already explained a few things. Okay, we explained alpha, which is the alphabet of propositional calculus. It defines all the most basic symbols that we will be using in propositional logic. So for the ones that we talked about would be 0, 1 for false and true. We have P, Q, R, S, T for variables. And then we have the Greek letters, phi, psi, and rho for what we call schematas. Okay? But I cannot explain what a schemata is until we get to the later part of this note here. The next set within the tuple that describes a particular propositional calculus system is omega. The omega is really, these elements of the omega set are connectives. But that really is a fancy word for operators. So as far as we are concerned, when you're dealing with logic, the operators would be and, or, not, and then we have implies and also is equivalent to. So those are the main operators that we use with propositional logic. So just fancy words, to describe, what operators are. They're called connectives in this case. But once we have, omega and alpha defined, we can also define what is a well-formed formula. Now, what a well-formed formula is simply something that is made out of elements from alpha and can potentially be connected by a connective in one of the omega sets. Okay. So, but because of the recursive definition, the second line, let me just highlight which line I'm talking about, and I'll magnify. But because of this particular definition here, we can make larger or more complex well-formed formulae out of the simpler ones. And that's why we can basically create an infinite number of well-formed formula based on just a fixed number of alphabet and a fixed number of connectives. Is that making any sense so far? Okay. But a well-formed formula is basically just a syntactical object. It has no meaning to it. Okay? In other words, we cannot really say, okay, is this formula true or false? Not even 0 and 1 have any meaning in this particular case. That's because these are all symbols. It's just syntactically defining what we can create out of the alphabet and also out of the connectives. So the next thing we have to do is to take a look at Iota. Okay, so Iota is the set of well-formed formulae that are known to be true to begin with. So these are basically the foundation of everything. In other words, it is also going to define the operators. It's going to define the connectives. In this case, we define 1 is true. We define not 0 is also true. Now, if I define not 0 to be true, it also basically means 0 itself is false. It defines the 4 combinations that you need. The 4 combinations that you need in order to define conjunction. There'll be another set like these for disjunction, another one for implication, and one for equivalence. So by using these particular equations, we are defining the meaning of the operators or the connectives. So this is what is giving meaning to the operators, because before this, the operators are nothing more than just syntactical things that you can use to make bigger and bigger syntactical thing. But this is what is going to give those syntactical quote-unquote things, which we call WFFs, well-formed formulae, actual meanings. Are we still doing okay so far? Kind of okay? All right. If you want to have one analogy, you can basically just imagine if we drag someone from, okay, I'll pick on art people. So if we drag someone from the Art New Media lab, which is right next door, 2 labs down from this hallway, and drag that person in and ask that person, what is this? That person would go like, well, it's A and then a little TP symbol and a B. What does it mean? That person would not know what it means, right? It's the same thing here. Without the iota set, this has no meaning. We know it is a well-formed formula, but we have no idea what it actually means. It is what we are highlighting here that gives meaning to this particular well-formed formula. Is that okay? Okay. So let's move on to zeta. And I think we went through a part of zeta, but not really the whole thing. So zeta is basically saying, okay, can we use existing formulae to derive a new formula? Okay, that is the question. Can we do inference? So the format of any type of inference would look like this. Every single rule of inference is going to look like this. On the left-hand side of this particular symbol, which is a inverse symbol, we have a set. This is a set of well-formed formulae. What that means is if every single well-formed formulae on the left-hand side is true, then we know for sure whatever formulae on the other side is also true. Okay? So the other thing you can also say is basically to say if psi 1 and psi 2 and psi 3 and so on, that implies, okay, if all of those psi with a subscript, if all of those are true, we infer that phi is also true. The other symbol with a circle and a stroke is phi. All right. Are there any questions about this particular notation? Because this is the foundation. This is the general template of what a inference rule should look like. Is that okay? Any questions about this part? All right. If there are no questions about this part, then we'll move on and talk about actual propositional logic. The actual propositional logic in terms of inference rule has something that is kind of interesting. For instance, it has something that looks like this. This is an inference rule that has nothing on the left-hand side, or you can say the left-hand side has an empty set. In other words, I don't need to know anything being true in order to claim, in order to infer that psi or not psi is true. Well, but does it make any sense? Do you need to know anything ahead of time in order to claim a particular well-formed formula or the negation of the very same well-formed formula is true? You don't. You do not. Okay? Now, how do we know this? You can do it with a truth table. So informally, I'm going to show you how to do this with a truth table. So the truth table is basically looking at psi as a single entity, okay, because it has a particular value. It evaluates to either true or false, okay? And the negation of psi is also going to evaluate to the opposite of what psi is. So now the question is, if I look at psi or not psi, what am I going to get? This is fading out. I'm going to try the other one. Okay, so let's say psi itself is false. Well, that would make not psi true. Is that making any sense? Because that's the negation. What is false or not false, which is true?
True.
It is true. Okay. Let's take the next one, which is 1 here and a 0 here. What is the result of this?
1.
It's a 1. Okay. What about the next one? Let's see. We have 0, 0.
Doesn't exist.
Okay. Cannot exist, right? Because this is not independent of this. So this cannot exist. Okay, fine. and 1, 1 does not exist either. So now we have looked at all the possible possibilities, and with all the possibilities, if you focus on this one single column here, psi or not psi has to be true. Do I need to know anything ahead of time? Do I need to know whether psi is true or not in order to know that psi or not psi is true? The answer is no. Is that making any sense? So that's why, as an inference rule, it looks kind of awkward. If I just kind of magnify this one more time or twice, it looks kind of awkward because it's basically saying from nothing, from knowing absolutely nothing, I can now infer that psi or not psi has to be true. Okay, now how useful is this inference? Well, doesn't seem like it's very useful, but it is there. The second one is basically the same thing, but it applies to conjunction. Now, I'm not going to draw out the actual truth table in this case, so I just go ahead and describe it. From nothing, from knowing absolutely nothing, I can infer the negation of the conjunction of psi and not psi has to be true. But that makes sense, right? Because when psi is false, not psi is true, but false and true is false. On the other hand, if psi is false, not psi is true, false and true is also false. But if you take the negation of the conjunction, then you get true again. So once again, we can get to this particular well-formed formula being true by knowing absolutely nothing ahead of time. It does not require anything to infer that. Is that okay? Now, what this psi is a placeholder. It can be any well-formed formula. It can be as simple as just a constant, 0. Okay? It can be a certain variable, which is P, Q, R, S, T. It can also be another well-formed formula. It doesn't even matter what it is. This has to be true. I mean, this entire thing has to be true. This one is kind of interesting also. This one is basically, this is a really important one. It is called modus ponens. And it is really useful because what it means is if you know that phi is true, and you know phi implies psi is also true, then you can infer that psi is true. Okay, so let me give you an example of what it means. Okay, so let's say I make a claim. Okay, so this time I have to pick a claim that is actually true. Okay, so I will have to pick a claim that's true. Okay, if the sky is blue, it is daytime. Okay, which generally is true. Okay, well, at least on Earth. Okay, so if the sky is blue, it is daytime. And then I add on top of that and say the sky is blue right now. Okay, so now you have two statements that are both true. One is the sky being blue right now, and the other one is if the sky is blue, it is daytime. So when you combine these two, what do you know for sure? What can you infer? It is daytime right now. That's basically what that inference is talking about. But this one has a very special name because it is a technique of proving. It is called, well, it's basically just going forward in proving, okay? A lot of proof techniques depend on this one, which is basically saying, okay, if I know a rule of implication of some kind, and I know the precedent of the implication is true, then we know the consequent of the implication has to be true as well. Yep.
Isn't that just like normal deduction?
It is normal deduction, but in this case, because I'm using the V dash symbol, the vertical bar and a stroke across, this is syntactic. Okay. So later on we'll talk about whether the syntactic transformation makes any sense, because I can make any syntactic transformation I want as a rule, but does it really match the meaning of the operators? Okay, so we'll deal with that later. But at this point, this is how inference works with propositional logic. Now, why are we focusing so much on syntactic transformation as opposed to the meaning of the operators at this point? What do you think is the purpose the ultimate purpose of propositional logic is what? Other than making certain people miserable.
It proves it, right?
To prove, okay? But for whom to prove?
For us to prove, for us to be able to understand when we actually look at this in real life, what it actually means instead of having to go somewhere else to find out.
Now, if it is only intended for us, it doesn't have to be syntactic, okay? It just has to go by the meaning of the operators. Go ahead.
Let's make it general so we can apply to like anything.
It is going in. The whole point about making this syntactic instead of just depending on the meaning has to do with automating the theorem proving. So that it's not us who are doing this, it will be the computer doing this. Because the computer doesn't really understand the meaning of much, right? I mean, the computer is really good at transforming things, understanding the structure of something and transforming the structure of something into something else. That's what a compiler is, right? But the compiler really ultimately does not know what you intend to do with the program. The meaning of the program is completely, just your thing as a programmer. But the compiler does not understand the meaning of anything. It just says, oh, if I see this kind of statement in C, I will translate that into those, assembly language instructions. That's basically what a compiler does. So what we want to do is to make this as mechanical as possible so that we can program computers, basically mainframes, with huge amounts of processing power, and say, okay, here are the axioms. This is the theorem that I want to prove. Now go at it. We want the computer to come back and say, no, this theorem is not true, or the theorem is true. That's ultimately what we want to do. So that's why we are focusing so much on the syntactic or the mechanical aspect of proving something, as opposed to, well, we understand the meaning of all of these things, so we don't need these formal rules in order to prove something is right or not. The next one is not as obvious, okay, but nonetheless, at this point, it is just a syntactic rule to basically say, if there is one well-formed formula already derived, already inferred, or it is an axiom that phi implies psi. So let me highlight which one. So once again, if tech claims if the sky is blue, it is daytime. Okay? But this time I also, for whatever reason, derive not psi. In other words, I can now say, it's not daytime. Maybe I look at my watch and say it's not daytime. What can you infer from these two well-formed formulae that are both true? They're both derived already. What do you think? So let me repeat what I said as an example. If the sky is blue, it is daytime. And I tell you it is not daytime right now. So what can you infer? The sky is not blue. Right? Does that make any sense? Sort of? Now this one also has a name. It's called modus tollens instead of tollens. I don't speak Greek, in case you wonder. So these things, this one means it's proved by contradiction. You can always right click and search for the. Oh, I misspelled it. It's double L and not single L. And for the most part, Wikipedia can be helpful. Okay, if you want to look up, what the meaning of certain words, it can be helpful. And you can also see, how it is defined here. It's basically the same thing of what we talked about earlier, except it doesn't use the V- symbol. Instead, it uses a single horizontal bar to separate, the given and what we're inferring. Okay, but basically, otherwise, it's the same thing. It's called denying the consequent, but it is the foundation of proof by contradiction. You negate something, and then you say, okay, if I negate it, then whatever is on the other side of the implication has to be false. Okay. Are there any questions about modus tollens? Okay. This one is trivial. This one is really trivial because if I can derive phi and I can derive psi both at the same time, well, it's natural that we can now say, the conjunction of those two is true. Because whatever I can derive is true. So if I can derive phi and I can also derive psi, then the conjunction of those two also has to be true. And then we have the last one, which is a simplification. This one basically says, if I know the conjunction of phi and psi is true, then I know for sure that psi is true. I mean, phi in this case, phi is true. But does that make any sense? Sort of, maybe. Do you guys want to see it in the truth table? No? Okay. So these transformation rules, some of these, well, not these, but some transformation rules can go both ways. So when they go both ways, I use this symbol here to basically mean they can go both ways. And these are basically equivalences. Okay, so when you look at these are all by definition equivalent to each other. This one we know already. Having phi implies psi is to say the negation of phi or psi. Okay, this is basically something that we already know. And then there's a whole bunch of these. We have the commutative law of conjunction. We have the associative law of conjunction, the associative law of, okay, misspelled here. Obviously copied and pasted, forgot to change one part of it. Is disjunction. This one should be disjunction. We have double negation. Okay, the double negation of something is just the original item. We have the distributive law of disjunction over conjunction, distribution of conjunction over disjunction, and then we have the 2 De Morgan's law. Those are the axioms of propositional logic. Are we doing okay so far with these guys? Does anyone want me to go over any particular one? No? You guys remember all of these things already?
True. That one.
Which one?
That one.
Distribution of conjunction over disjunction. Okay, so let's go ahead and play with that one. Okay, so let's take a look at this one. Okay, so this is related to the distribution of, distribution of addition over multiplication in normal arithmetic. Okay, but let's see how it works in this case. All right. So what I'll do is, instead of using, well, do you guys want me to use the Greek symbol, or do you just use regular English symbols? Because I can use either one.
Up to you.
Say again?
Up to you.
Oh, okay. So I'm going to just use PQR, okay, because it's just easier that way. So we have P, Q, and R as independent variables. So these three have nothing to do with each other. So when P is false, Q can be false or true. When Q is false, R can be false or true, and so on. So now I can make a truth table. You don't have to copy the whole thing. You can probably find it somewhere. Okay. But the idea is to generate a truth table based on the number of independent variables. Okay. The key is these three have to be independent, because otherwise I cannot make a full table like this. The next thing we have to do is to evaluate one side of the implication or the inference. So we'll look at this one first. So we have P, or, Q, and R. Okay. So we'll evaluate this expression for each row. For the first row, it means P is 0, Q is 0, R is 0. 0 is false. So without even looking at this one, we can say that it is false. Okay. The second row is P is false, Q is false, R is true. That's not going to help, right? And then we have Q being false, Q being true. That's not going to help. Now we have Q and R both being true. Yep, that will help. And then we have P being true for the next 4 rows. That's all we need in order to turn the entire disjunction to true. So we have 4 ones down here. Okay, so that's not really difficult. It's really a lot of chore, because you have to evaluate the expression for every single row and come up with the actual answer for each row. And then what we do is we look at the expression on the left-hand side of the double-sided inference. And then we say, okay, so now we have, P or Q and P or R. That's an interesting ringtone. That's okay. All right, so let's take a look at this one. So when you look at this one, if P, Q, and R are all zeros, okay, most people can say the first one is going to be a 0. It's going to be false. The second row, we have R as being the only one being true. So this is true, and that turns this entire disjunction into true. But this side is still false, and with the conjunction as the loss operator, we have false and true, so the whole thing is still false. False, right? Because it's a conjunction. It's symmetric to the next row, so the next row is going to be a 0 because the next row has Q being the only one with true. So we have this side being true, this side being false, true and false is false. Now we have both Q and R being true. So if Q is true, this is true. If R is true, this side is true. Then we have true and true, so this is a true. And then for the next 4 rows, it's pretty easy because P is on this side, P is also on this side. So if P is true, the whole thing is going to be true. So we just stick 4 ones down here, right? So are there any questions about the truth table at this point? All right. So with this entire truth table, do you notice anything about the last 2 columns, being this expression and this expression? They're always the same, right? In other words, I can look at this in 2 ways. I can say every time we have a 1 or true on this column, the other one is going to have a 1. We can also look at it in the opposite way, which is to say every time the second column has a 1, we know the first column is going to be a 1. That's why it goes in both directions. When it goes in both directions, we say these 2 expressions are equivalent to each other. Because when they're false, when one is false, the other one has to be false. When one is true, the other one has to be true, and it goes in both directions. So is that helping? But this is actually, we are moving one step ahead of time right now, because what we see on the projector right now, which is the highlighted portion here, is syntactic. It basically says, if you have a regular expression, well, this is not actually a regular expression, but if you have a parser, okay, that can recognize this structure on one side, then you can basically infer this and say that this has to be true as well. And it is completely syntactic. Yep.
What does the H-looking character mean again?
It means infer in both directions.
Okay.
So look at that as the combination of this, which is inferring the left is inferring the right, and combining that with this, which is inferring the left from the right.
Gotcha.
So when you combine those 2, it looks like an H. All right. So are there any questions about these inference rules? Okay, with an emphasis that each inference rule is a syntactic rule. Okay, it will take a compiler type of thing to analyze a well-formed formula and recognize, hey, I can see this a particular well-formed formula this way, and now we can infer that that has to be true too.
So is Zeta like the set of all transformation rules?
That's a good question. So the question is, where do we get a set of all the transformation rules or the axiom, the transformation axiom? This may or may not be complete. I'm not 100% sure, but I will show you another slide, that I just linked to from Moodle today, and that one will give you a whole list, and then we can add to this. Okay. All right. So let me do that first, so that we know where to find the axioms. So we'll go ahead and go to. I'm sorry about all this scrolling. Oh, where is it? Next one. Propositional logic axioms. This is just a link to some other website. But on the other website, it does give you. 5. There we go. So this is, this is a link to somebody else's website. These are the axioms of propositional logic. You can see that most of these things we have talked about already. P and Q is equivalent to Q and P, which is the commutative rule of conjunction. Disjunction is the same way. And equivalence also has the same rule. Okay, we can go in both directions. And then we have associativity, which is basically saying you can move the pair of parentheses when you have a sequence of conjunction, and you can do the same thing when you have a sequence of disjunction. Then we have the distributive laws that we just talked about a little bit earlier. And the funny part is in propositional logic, it goes in both directions. Because in arithmetic, you can only distribute addition over multiplication, but not the other way around. But in logic, okay, in Boolean algebra and also in propositional logic, it goes in both directions. And then we have De Morgan's law, okay, which is what we talked about earlier. Negation, they looked at this as an axiom, okay. And then we have this one here. We have seen this one already. Remember this? This is deriving or inferring psi or not psi from nothing. Okay. And then we have the equivalent of this one with conjunction, which means psi and not psi has to be false, or we can say that we can infer the negation of the conjunction is true. And then we have implication. We talked about this one too. This is actually the definition of equivalence. Equivalence is if P is equivalent to Q, it is basically the same thing as P implies Q and Q implies P. Or simplification and simplification. If you have P or P, it is the same thing as P. If you have P or true, it is true, and so on. So this is a full set of all the axioms, and every single axiom can turn into a transformation rule. Are there any questions? I was just being lazy and not really want to type in all the transformation rules. Because that's not really the main purpose of what I am trying to teach here in this particular note. So let me go back to this note here. Music? Maybe. Okay, so getting back to the stuff that I wrote, the focus is not so much on the transformation rules, but the concept of it. So we are moving on to talk about the soundness and the completeness of a formal system in logic. Okay, so what is the soundness and what is the completeness? In other words, it has to do with, does it make any sense? Soundness is whether the syntactic mechanical rules make any sense or not. Because I can pick up any transformation rules, right? If I feel like it, I can do something like this, which is complete nonsense, okay? I can say P and Q transforms to not Q, that's it, okay? Which makes no sense, right? But this is mechanical. Remember, this symbol means we are just mechanically looking at something that has a structure like this and infer something like this. But it's a structural transformation. It doesn't have to make any sense. So when we look at a system like this and a transformation rule like this, then we'll say, hey, this does not make any sense. But how do we, quote unquote, qualify this particular transformation rule as saying, hey, it does not make any sense? Well, it does not make any sense because of the meaning of the conjunction operator and the negation operator. Okay? Given the definition of the conjunction and the negation, this makes no sense. So how do we check a system and say, well, how do we know the system as a whole is sound, which means it makes sense? The other word, which is completeness, is basically saying, is it enough? Is the mechanical system sufficient to represent everything that we can express in according to the meaning of the operators? So that relates to your question earlier. Okay, the question earlier was, is that all the axioms? Okay, remember that question? That was a really good question, because if I do not capture all of the meaning of propositional logic in the mechanical rules, then there are things that is actually true, but I cannot derive it, because the mechanical inference does not have enough tools to get to reach the conclusion. Okay, so that is also a very important question, is it complete? If something is actually true, can I prove it mechanically using the inference rules? That is the completeness. So there are two ways to look at what we are dealing with here: soundness and completeness. The rest of this is really just a description of what I just said, so I'm not going to repeat it. So before we can talk about whether a particular system is sound or complete, we have to kind of look at a few things first. The first one is called semantic entailment, okay, which is really big words, right? The big word, basically means semantic entailment. Basically means according to the meaning of the operators, the connectives, is a particular transformation rule matching the meaning of the operators. That's basically all it's saying. Okay. So let me pick one particular rule. I'm not going to read all this stuff first. I'm going to give you an example first, and then we'll read all this stuff. Because if you read all this stuff first, it's not going to make a whole lot of sense. In other words, it's not, sound to begin with. Okay, so we'll go ahead. I'm going to erase this, and we'll start with something that may be a little bit easier.
Would it be possible to do it on the screen?
Projector? Oh,
Yeah.
sure. I'll give it a try.
Unless you're using lots of fancy symbols.
Fancy symbols. We'll just try to use mouse pad. Okay. All right. So what we'll do is we'll pick one of the inference rules and say, okay, but does it make any sense? So we'll pick this one here. Okay, I'm just because I cannot type the negation symbol and stuff like that. I'll just use the English word here. So not phi, okay, which is representing the symbol phi, and I'll use this approximation of the inference, okay, and it infers phi. Okay, so this is an inference rule. Basically, it's saying if you see the double negation of any well-formed formula, drop the negations, or I can drop the negations if I want to. Is that okay? Now with this one, it actually goes in both directions, but I'm just going to show one way first. Okay. All right, but this is a mechanical rule. Okay, it's a mechanical rule. I don't know whether it makes sense or not. So how do I show that this mechanical rule is consistent with the meanings of negation in this case? Because we only need negation to look at this rule. All right. Any questions? Go ahead.
Could you do a truth table?
Yep, that's what we'll do. We'll do it through a truth table. Okay, so we'll do it through a truth table. So a truth table in this case only has one single variable. Okay, because we only have phi here, and next to it will be not phi. And I'm just doing this in multiple steps. You can combine the steps into one if you want to, and then not phi. Okay. Because we only have one single variable, there are only two rows to consider, because phi can either be false or true, okay? Cannot be anything else. If phi is false, not phi is going to be true, and if phi is true, not phi is going to be false. But if not phi is true, not phi is going to be false. And the other one is going to be a 1. It's going to be true. Okay, sorry? So the requirement for the inference rule to make any sense is to say, if I look at this column corresponding to the left-hand side of the inference, if I can spot any row that has a 1, which is this one here, does it automatically make the other side a 1? Well, yes it does. Well, so I have just proven that this particular inference rule is sound. Or I have shown, okay, I'll take it back. I have shown this is semantic entailment. Okay, so the other way to say this, once I have a truth table to prove this, so now I can say not phi semantically entails, which is very similar to infers, but it's slightly different. It has 2 bars instead of 1. So the notation to mean not phi semantically entails phi is this symbol here. Is that okay? Sort of. So let me get back to the notes so that you know which part of the notes is talking about this. Okay, so we'll kind of ignore all of this nonsense first because it really looks like a whole bunch of stuff. We can get to this part here. So this is the symbol to represent semantically entails. And to prove something is semantically entailing something else, you have to either use a truth table or you can use the function approach to do it. The function approach is really kind of long and tedious. The truth table is much easier. So I would just use a truth table whenever it's possible. Okay. Are there any questions? Well, here's the next question. Why do I use, should I use phi or should I use PQRST? In other words, what is the difference of using a Greek symbol as opposed to using a letter from PQRST? Okay, so I'll go back to the mouse pad here to kind of talk about that. Okay. So what is the difference of saying this instead? Okay. Well, if you remember, in the alpha set, all the Greek symbols are representing well-formed formulae. Okay, each one is representing a well-formed formula. Okay, but a well-formed formula can be many things. It can be just a constant, it can be a 0, it can be a 1. It can also be a variable. It can also be a combination of stuff. It can use connectives. On the other hand, if I have just a variable is a variable. It can range over all the constants, which in this case are 0s and 1s, but it cannot be made out of connectives. So that means if I make my syntactic rule or my inference rule like this, it will only be limited to say this applies only if you're dealing with a particular variable p. That's it. Okay. What about q? If it is not q, can I infer q itself? No. This inference rule says no. Okay. It is only applicable to that particular variable p. But I don't want my inference rule to be that specific, right? Because I want my inference rule to be as general as possible. And that's why the inference rule is using a Greek symbol instead. It is basically saying if phi is any well-formed formula, okay, which means it's made out of the elements of alpha, and using connectives, structurally, make up really big things. As long as phi is a well-formed formula, and not phi is somehow inferred, okay, I can infer phi, not phi itself, then I can infer just phi. Is that making any sense? But that's really helpful because now it is much more general. It does not apply to just one single variable or just variables anymore. It applies to all well-formed formulas. When we talk about semantic entailment, it really is not defined this way. Okay, it really is defined to basically say if phi makes use of any variables, p, q, r, s, t, then this claim, okay, the truth table they have to match regardless of the values of the variables. That's why when you look at the actual definition of semantic entailment in the description here, it's a little bit more complicated. Okay, and I have been trying very hard to give you an example of how to use this particular definition, and I still have not come up with a good example yet. So I'm gonna skip this part for now and just basically say you can use a truth table on the Greek symbols in order to prove semantic entailment. Are we doing okay so far with semantic entailment? Any questions? It simply means, by using the meaning of the operators, can we show that one thing implies the other? That's basically what it is. So once we are done with semantic entailment, which is really long, but it's kind of the same thing that we have that I've been using on the board. Then we can talk about syntactic entailment. Now, syntactic entailment is something that we already know, that we have dealt with already. It basically is just saying this, okay, which is saying, mechanically, we are deriving from phi 1 all the way to phi n to psi 1. Or psi, actually, the other one is just the mouse cursor. But this one is a little bit more inclusive, because this is not really referring to an inference rule. It is basically saying, through inference, okay, not in one single step. If you start with, these things, and eventually you arrive to this one here, then we can still say that these components syntactically entail this particular conclusion. So it does not have to be in one single step. You can have many, many steps in between, but as long as you can make that connection, it will still be semantically entailing the other one. Are we doing okay so far with this? Okay. All right. So if this is okay, then we can now define what is soundness. When you say a particular formal system is sound, it is basically saying anything that can, okay, you're basically saying this statement here. Okay, so I'm just going to look at this statement here. It's basically saying if you can mechanically infer something, it automatically also means that semantically it also has a semantic entailment. Is that okay? So if mechanically you can make an inference about something, then automatically you can also it implies that according to the meaning of the operators, you can also prove that one can show the other, one will imply the other. Any questions about this? Okay. This would fail that. This is not sound. Okay, let's go ahead and look at this one and see why it is not sound. Okay. It is not sound because this is a mechanical rule, okay? And in any system, if I can, say that, okay, P is true, Q is true, this is just mechanically saying that the negation of Q has to be true. But this is mechanical. So what I will do is to see whether the left-hand side is also semantically entailing the right-hand side. So we can do it with a truth table. This one's pretty easy, P and Q. And then on the other side, we have just not Q. We have two independent variables, P and Q. So P, Q here. Now because we have two independent variables, we have 4 rows in the truth table, because 2 to the power of 2 is 4. P can be false, P can be true. But when P is false, Q can be false or true. When P is true, Q can be false or true. Okay. I'm sorry, I'm using the whiteboard again. So when you look at just P and Q, okay, this is false, 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 true. That's just a definition of conjunction. When you look at the negation of Q, it is going to be 1, 0, 1, 0, because it is just the negation of Q. In order for the left-hand side to semantically entail the right-hand side, every time P and Q is true, not Q also has to be true. So now we look up all the rows and say, okay, when is P and Q true? Well, we only got one row that we need to focus on. P and Q is true only when they're both true. What about not Q? It is false. So it is not semantically entailing the other one. And yet, I have this stupid inference rule here. So now I can no longer claim whatever is highlighted on the projector. Because on the projector, I have this thing being true, but then I have the other one, which is P and Q, semantically entailing not Q. This is false. True implies false, is false. So that means this is not a sound rule in the system. And the system as a whole, if it does have a syntactic or an inference rule like this one, then it is also not sound. Yep.
So mechanical rule is just the steps to show that something is true.
The mechanical rule, which is inference using the single bar, is basically just saying in a formal system, the formal system is really just a syntactical manipulation system. All it does is to say, okay, can I recognize this structure on the left-hand side? Oh, if it does, if I can recognize this on the left-hand side, then I can transform it or infer whatever is on the right-hand side. Okay, but it's a syntactical thing. It has nothing to do with the actual meaning of the operators. So I can come up with something like this by mistake and say, well, that looks good to me, and program that into the system. But it is not sound because it really does not match the definition or the meaning of the operators.
So it's kind of like a transformation, like De Morgan's law could be like a mechanical rule then.
De Morgan's law is a transformation, but it makes sense only because of the meaning of conjunction, disjunction, and negation. Is that okay?
I think so, yeah. It just had to be a little more abstract, I think, than a...
Right, because you can claim inference, using really kind of odd and incorrect cases. It is really nothing more than a find and replace, if you will. It says find P and Q, replace with not Q. But this one does not make any sense because of the way we define the operators conjunction and negation. Now, in the case of De Morgan's law, it is also something like that. So if I roll back to the De Morgan's law transformation rule, okay, so we'll focus on just one of them. Okay, we'll just focus on this one here. This is basically saying find and replace. Find whatever is on the left-hand side, replace with the right-hand side. Because it's both ways, so you can also say it is also saying find the right-hand side and replace with the left-hand side. But this one is sound because I can actually prove, according to the meanings of conjunction, disjunction, and negation, it is the columns match up. Is that okay?
Yeah.
Okay. Any other questions? No other questions? Okay. So we'll go through the last one, which has to do with completeness. So completeness is kind of saying, the syntactic transformations are sufficient. Now, what do we mean by it is sufficient? It means that if a particular well-formed formula semantically entails another well-formed formula, we also want the mechanical system to be able to infer the conclusion from the premises. That's basically what it is. If a system is sound but not complete, then there will be theorems that you cannot prove. Even though it is true, the mechanical system cannot come to the conclusion if it is not complete. If it is not sound, then there will be theorems that you can prove, conclusions that you can reach out of the mechanical system that does not make any sense, that is actually not true in real life. So by combining soundness and completeness, we're basically saying the two systems, one is mechanical, which is just mechanically or syntactically looking at things and transforming things, is actually truly equivalent. It is representing the semantics or the actual meaning of mathematical operators, or logical operators in this case. Are we doing okay so far with this? And remind me again, why is this stuff important? Why are we doing this? We talked about it a little bit. I just want to see if you guys remember what I talked about.
Computer-generated proofs.
Yep, we want to be able to program computers, input all the inference rules, okay, and input of the Iota set, the whole thing, the 4 sets of stuff, and then just give it a theorem and say, I suspect this is true, okay, and then just present it to the system and say, prove me wrong or prove me right. Either way, I want to know. That's what we want to do. And that's why we want to talk about inference as a mechanical transformation, and we also want to talk about soundness, which basically means, are the transformation rules making any sense? This one does not make any sense. And we also want to talk about completeness, which means if something is actually true, can the mechanical system come to that conclusion? Yep.
So if we feed a computer things that are nothing but sound, it will give a sound response?
That is correct. Okay, so if you have a propositional calculus system, which is a formal system, it's completely mechanical. You only give it sound inference rules, okay? Then the conclusions will always be sound. Whatever conclusion it reaches is actually true. If it says your theorem is true, the theorem is actually true. But if you don't give it enough inference rules, in other words, it is incomplete, then there are theorems that it cannot prove because it doesn't have the tools to get to the theorem, the conclusion that you want to reach. So it will give you false negatives, which means it will tell you something is not true or not provable when it really is actually true, because according to the meaning of the operators, it is actually true. Is that making okay? But that's not good either, right? A false positive is not good. If the system is not sound, then it can give you false positives, which means it can give you a conclusion and say, yeah, that's true, but in reality it is not. So that's why you want it to be both sound to eliminate false positives, and also complete, which eliminates the false negatives. Then you have neither false positive nor negatives. That's a good question. I never really thought about it or tried to explain it that way. So it's because of your question that I kind of, okay, well, that's what it is.
You make us all smart.
Hmm?
You said you make us all smart.
No. You made me smart. Well, you made me smarter. I'm never smart. I'm just smarter than before, like a few minutes ago. It's always just the delta. Right. So, are there any questions about this slide here? Just about propositional calculus. I think the most important part is really to understand its significance. Why do we talk about it in a computer science class? Because it sounds mostly just like a math class stuff, right? I mean, it's just conjunction, disjunction, all the truth tables and stuff like that. But the reason why it is important is because in computer science, we have a holy grail called automated program verification. Okay, imagine this, okay? Imagine this. Imagine someone at, let's say, Microsoft, okay? They come up with a 4-page description of the correct behavior of the anti-kernel, okay? And then they throw the complete source code of the anti-kernel into the system, along with the description of what is correct. And after 30 seconds, the system comes back and say, nah, it's not doing what it's supposed to. Or it can come back with an answer if Microsoft spends enough time to fix all the holes, all the bugs and whatnot. It can come with an answer and say, yes, this source code will do what the other description is describing that it should be doing. Wouldn't that be nice? That's called automated program verification, and you can probably look that up. It's a really, really old branch of computer science. It's nothing new at all. It's called automated program verification. Formal verification is just the other name of it. But you can see that it's nothing new, and even Microsoft Research has something to say about it. Slayer, which is kind of a ironic name. And they have other acronyms like SLAM and BLAST. Somebody is having fun with all the acronyms. Yep.
So is it like fuzzing, where you're just trying to give it as many inputs as you can?
No. This is the opposite of fuzzing. Okay. Okay. That I'm glad you brought it up. Okay. Does anyone know what is fuzzing in computer security terms?
It's when you just constantly give something input over and over again.
You're jabbing a piece of software until it breaks, until you find the security hole. Okay, so okay, this is good. I think this is actually very much related to this class. Instead of making this class, really dry and boring because it's all math and whatnot, this is actually useful. Okay. Okay, so fuzzing is a software testing or breaking or hacking technique, often automated or semi-automated, that involves providing invalid, unexpected, or random data to the input of a computer program. All right. So with a focus, okay, let me highlight the key word here. Okay, keywords, fine. 2. In other words, you are not testing whether the software works correctly when the input is as expected. You are particularly specifically testing it, you're particularly testing what the program is going to do when you present something that is unexpected, something that is out of specification. Okay? Now let me give you an example. Okay, example, FTP server. Okay, I'm hoping most of you know what FTP is, or at least have an idea of what it is. It's file transfer protocol. It's nothing more than a protocol that says, okay, with a header like this, and a length of like this, and a request like this, and blah, 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 the other side should do something like that. Okay, it's really just a way to transfer a file. It's a very, very simple protocol. Now, within that protocol, there will be expectations, like the length of each packet is supposed to be like this long, okay? Or this part of a packet can only have this many characters. The file name can only be this long, and so on and so forth. There will be limitations and specifications. You can only use these characters as a part of the file name, for instance. Okay? So there will be something to be expected by the server, and say each request, each well-formed request should look like this. Okay? So what fuzzing is going to do is to specifically looking at the specification and say, I'm not going to follow these rules. In fact, for each rule specified, I will try my best to find the maximum numbers of breaking those rules. And then it will, for each case of breaking the rules, it will format an actual packet and send it to the FTP server. And then it will observe what the FTP server is going to do about it. Okay? Now, if the FTP server is implemented correctly, then every single time it will either not do anything or come back with an error. But if the FTP server is not checking correctly of all of those cases, then sometimes it will do something that is quote unquote unexpected, something that the server really should not be doing. Is that okay so far? And that's something that the server is not supposed to be doing can be a security hole. In other words, it may be a chance for you or a hacker to slip in some payload code into a intentionally malformatted packet, and therefore indirectly using the FTP server to gain control on the server. Is that okay? That's fuzzing. Automated theorem proving is the opposite of this in all imaginable ways. Okay? So what do I mean by all imaginable ways? First of all, when you have program verification, you focus on valid and expected, but not only about the input, but also about the output. Okay, so you're basically saying if it is presented with this kind of data, it should have that kind of output, and you can program in what it should be doing with invalid and unexpected input too. You can basically say if the input has some characters that is not supposed to be presented, it has to return this particular error. It's kind of like when a web page is not found on the server, you get a 404. Okay, that is an expected response from a request that is not making any sense. Okay, that is unexpected. So you can program in all of that stuff and specify the actual behavior, the correct behavior of the software. But the part that is also opposite to fuzzing is we are not going to present random data to the system. We are going to mathematically prove the system, step by step, one line at a time, that what you describe as the correct behavior of the program is in fact what the program is going to do. Are we doing okay kind of so far with this stuff here? So you can kind of imagine if fuzzing is an attack strategy, then automated theorem proving is a defense strategy. Okay? This is basically looking at a shield, okay, and keep poking at it until it finds a weakness, a weak point to punch through. That's what fuzzing is about. And obviously, if that is what fuzzing is about, and it is only semi-automated, that means the more havoc you have in terms of number on the attacking side, the better they are off, right? Because now they can parallelize a lot of different techniques and a lot of different ways to break a program. Automated theorem proving or automated program verification is on the defensive side. It is looking at a shield and analytically, structurally analyzing the shield by its design and say, by design, this shield cannot have any flaws, okay, because of the way it is constructed. So automated program verification is very much related to computer security because it is quote unquote the ultimate shield. Look at it as Captain America's shield. And then the other one, which is fuzzing, is Wolverine. You guys are not responding. You guys don't watch all that stuff? No? This is Wolverine poking his claws at something. Whereas, automated theorem verification, automated program verification is Captain America trying to fend off, Wolverine with his shield. Yep.
But isn't the automatic theorem testing basically like your comparison of the dartboard testing, like one input and then like
no,
yes, that's correct.
It's very much the opposite of the dartboard testing.
But like how is that done in practice then? Like how do you?
In practice, we don't have enough horsepower to do automated program verification. So that's why it's called a holy grail, at least up to this point. But it doesn't mean that we have to give up, the holy grail and say, we cannot do it, okay? Because there are many things that we could not do before, okay? I'm pretty sure I used this example before. At the end of World War II, we got computers, we have airplanes, but no one has ever thought about, an automated airplane with a computer on board and the plane can fly itself. We talked about that already. Because you cannot fit a computer onto an airplane. That's it, okay? Just physically, it is impossible. And when you talk to the people in the 40s or the 50s and say, maybe eventually computers will be small enough to fit onto an airplane, they will all go like, you're crazy, it can never happen, right? But today, you can put a computer onto not a normal sized airplane, you can put it onto a remote control airplane, a drone, okay? And have the drone to kind of fly itself to do stuff, right? So what is it, so how does it relate to automated program verification? Just because we don't have the horsepower today doesn't mean that one day we will not have that horsepower to do the same thing. So that's why it is still an interesting research area. And as I said, originally it was not intended for computer security. Okay, originally it was really just the holy grail because people want to make sure that the code and the program, the source code, is correct. Okay, so it was the obsession of perfection that kind of stemmed the whole area of automated program verification. Yep.
So does that mean if we ever get to a point where we could do this, then there could potentially be no more hackable systems?
At least not in the sense of hackable today. Every system is hackable in one form or another, and in many cases it's the human factor that makes it very, very hackable. It's social engineering that does most of the hacking. But what this means, if automated program verification becomes reality, it simply means that fuzzing is not going to work anymore because there will be no holes that you can find. Yeah, go ahead.
Well, I was trying to figure out, so does fuzzing go against axioms too? Like, if there's a built-in thing that says that if P, then Q, will that go against it, saying that if P, then not Q?
Not really. What fuzzing is about is breaking rules. But those rules are not the propositional logic rules. Those rules are basically rules of a protocol, like FTP has specific rules, has a specific set of specifications. So you're intentionally going out of specification and see what the other system or the system being tested is going to do. Yep.
says you can apply fuzzing to hardware as well.
You can fuzz hardware as well, and that's how people break the firmware out of chips of basically all kinds. Okay, let me kind of roll. Sorry.
Like custom firmware, like
Custom firmware, like ECU, engine control computers, ECU control unit. Okay, so engine control unit is basically a small computer inside your car, and its job is to look at the oxygen sensor, the mass airflow sensor, look at the temperature of your combustion chamber, knock sensor, and all kinds of stuff like that, and then it will determine the trim, basically what is the fuel to air ratio, going into the engine, and timing of the spark plug and stuff like that. So that's what the ECU is supposed to do. And most manufacturers don't want you to mess around with the ECU firmware for two reasons at least. One is it is proprietary. Okay, they don't want a competitor to look at the ECU programming and say, oh, I can now copy the approach of the other manufacturer and make my cars more energy efficient. Okay, and the second thing is liability. They don't want Joe Schmo to reprogram the ECU and say, when I press this button, it's going to dump a lot of fuel into the engine. Okay. So if they want to protect that code, right? Most MCUs are microcontroller units. Basically, they're computer on a chip. Okay. Most of those MCUs have a feature that has a fuse bit, so to speak. It's a single bit, a 0 and 1, that you can program, and if it is programmed, you cannot read back the source code. You can just reprogram the whole thing, but you cannot read back what is already on it. So that will allow your distributors, okay, the car dealerships, to help you update the firmware on the ECU, but no one is going to be able to read back what was on it before you reprogram it.
What did you say that was called?
A fuse bit is basically just a 0 or a 1 that you can program on an MCU, but it's not a part of a program itself. It is basically a circuitry that is outside of the actual software, but it is quote unquote programmable by using usually a serial protocol to change it.
So that's why they always have to reset everything on the car, like the chips and the keys. Like when they reset those, they always just delete everything and boot.
Right, because they also have encryption, and it depends on the manufacturer. Some manufacturers are very anal about protecting their modules. So Volkswagen US is one of those manufacturers. So a regular mechanic cannot just replace a particular module and expect the thing to fit in and work as expected. They have to actually key in the actual unlock key in order for the module to talk to the rest of the system. So anyway, so they don't want you to look at the source code of the firmware. And what they do about hardware fuzzing is, okay, now how do you fuzz hardware, right? I mean, fuzzing software means if the packet size is supposed to be 128 bytes, you try something bigger, right? 256 bytes and see what the program is going to do. So with hardware fuzzing, what they do is they look at the VCC voltage specification. So for a part that is supposed to work at 3.3 volts or above, they will give it 3.2, 3.1, 3.0, 2.9. Okay, so they're fuzzing with the actual hardware characteristics. Okay, if a clock cycle is supposed to be 50 nanoseconds, wide, they would try 49, 48. So they're trying to break the hardware, but only at the at the boundary of something that is actually legal, and then observe what the chip is going to do. And they found out that a lot of chips can be quote unquote unlocked by doing something like that. Yep.
It causes a vulnerability to happen, so that you can inject your own code into the chip. That's like when you, for instance, like with laptops is a good example, especially newer ones with Windows 8. You're not supposed to be able to get a different BIOS that's unlocked. However, like in computers, they'll just sit there and play with the voltage on the chip until it fails, and then they'll inject their own stuff into the EC hardware so that it can get its own custom BIOS.
Correct, because at a certain level, if the design is not done right, when the input voltage is below a certain level, the locking logic doesn't work anymore. So you might still be able to get the content of the firmware, even though the fuse bit is saying, no, we should not disclose the firmware. The reality, some people have looked it up online, and I have the opportunity to look it up for somebody. And the reality is, if that doesn't work, if actual fuzzing doesn't work, they have techniques to file off the material on the chip itself until the circuit, until the silicon is exposed. And then what they do is they use a microscope and a laser to physically, remove a fuse bit. Okay, so that means nothing is protected whatsoever in terms of firmware and stuff like that. It's only a matter of time before they can break it. So when people say, I'm going to protect my firmware of whatever they're trying to control or whatever they're trying to release, they're really just messing around with how much time it will take for hackers to break it.
It's all about time complexity. It's all about time complexity.
It's all about time, and also about how exposed is your product. Because if your product, if you only sell 200 of your products per year worldwide, and each unit is only $200, nobody's going to waste their time to break your product because it's not worth it, right? On the other hand, if you're making something that you sell in millions and each one is worth $200 or $300, then suddenly it's worth the time to try to break it, because now you can sell counterfeit products or clones of that product, and it will still be worthwhile to break it. So I'm hoping that you guys think that I'm training you guys to be hackers, because that really is the intention. We don't have enough in the United States. Did I show you guys about the live picture?
Yeah.
Well, that kind of shows you why.
I found out how they track that too. Basically, they have their agents at different gateways in different countries, and it tracks the traffic across those gateways. Yeah.
So, but if they hack the gateways, then something can go unreported.
Correct.
So they need a control system where they intentionally plan something that will launch a certain attack to check whether the gateway is still catching it or not.
Good question.
Yep.
So fuzzing, though, is based off the assumption that there is an inherent vulnerability. Correct?
Yes.
Okay. So with formal verification,
You're taking that out.
you're taking the inherent vulnerability out. But in order to hack something that's formally verified, you just have to be faster than the formal verification process itself.
That is true. If the formal verification process is slow and people release software before they are formally verified, then it is just a matter of, it's a race, okay, it's a time race. On the other hand, if companies only release products that are formally verified, then there's no window for someone to hack into it.
But wouldn't it be more cost effective to release something and have it formally verified while it's live?
Well, then it depends on what you're talking about. So I'm going to leave this in your thoughts for over the long weekend, okay, along with the rest of this discussion. Yes, go ahead.
So just to make sure there's nothing that's been formally verified yet?
Maybe very trivial systems, but not anything that is of significance.
Something that's formally verified that doesn't need to.
Okay, so I'm going to leave your thoughts. Hey, we still have 2 minutes. So this will only take you a minute and a half. Okay. Okay. This is a X-47B automated drone that can launch from a carrier, which is what it's doing right now. Now, as I said, it is fully automated, which means once it knows its mission, it does not require someone to be remotely controlling it, and it can finish the mission
Skynet.
by itself. Okay? So, but it doesn't, so the control system is not a human being. Neither is it a magical being of any kind. Okay? So there's no elf or gnome or anything on it. It is a computer. And computers run on software, right? There's a program running on these things. And this particular program is unlikely to have gone through a formal verification process, which also means it probably has security holes. Is that okay so far? If it has security holes, it can be hacked. If it can be hacked, it can be controlled remotely by someone who is not supposed to have control over these things. Are you guys still following me? Okay. So that is an interesting thing, because that means if a particular country is really good at manufacturing weapon hardware, and automated ones at that, okay, but has a relatively weak computer security, force, then that country can now be manufacturing hardware for somebody else and not know about it. You guys still following me? So making things like this is great. Okay, on paper, it is the best thing to do because it is fully automated. People can shoot it down, and no one's gonna die. But in reality, it's opening a huge can of worm because if someone hacks into this, very bad things can happen.
Assuming it doesn't explode.
Yep.
See with the students, I think they're at the University of Texas, were able to hijack, they were paid by the military to do it, but hijack a military predator drone, just to show that it could be done.
Oh.
They just spoofed the GPS signal and pretended it was in a different part of the world than it really was, tricked it into traveling a different course.
Yep. So that means there's not enough onboard verification of its current location. It can be tricked.
This is the future. This is the future of war.
This is the future of war, but we just don't know who's the receiving end of it. All right. Well, this is all I wanted, kind of give you. But I think this is actually a really good important part of this class is.